Today's lesson is in Chapter 1. We will be talking about algebraic expressions, real numbers, like terms, matrices, and we will also introduce equations. To do this lesson, you would need to print a copy of the PowerPoint that I will be using. It will also be a good idea to take the same notes on the PowerPoint that I am writing on here for you, so you'll have that as a reference. It's best to always write in pencil when doing math. Once you have those materials, you'll be ready to begin. Let's get started. An algebraic expression is a mathematical phrase that includes numbers, variables, and operations. Operations mean addition, subtraction, multiplication, and division. However, there will be times in math where you will see the sentences actually spelled out in words instead of just seeing numbers and variables. Therefore, we need to know what those words represent. A word for addition is sum, plus, increased by, and you will also see more than. More than is a special term. It's called a switch term, and we will talk about that later, so you might want to put a star beside that. Subtraction would be difference. It could also mean less than. Decreased by. You could also see subtracted from. And again, less than was one of those terms that we should star because that's a special term. When multiplying, you could see product. You may also see times or per or each. Okay, divided by would be quotient. Maybe you would see it over if they were talking about a fraction, or simply divided by. Another important word that doesn't necessarily fit in either of these categories would be quantity. And what quantity means are something will be written inside of parentheses. Quantity is a term used for the grouping symbol for parentheses. So now let's talk about some examples. Okay, so let's talk about some examples of algebraic expressions. Remember that we had discussed on the last slide that more than was a special term for addition. What more than means is it is a switch term, meaning that whatever is before more than trades places with whatever is after more than. Therefore, if we're writing 12 more than a number out in actual numbers and variables, it would be x plus 12. It's also important to recognize that whenever you see the words a number, you cannot insert your own number there. What a number stands for is a variable. That's why we used x. You could pick any letter in the alphabet, that's perfectly fine. The difference of a number and 5. Well, difference is not a switch term. However, it does tell us that we are subtracting a variable in 5. So we could say v minus 5. The product of 10 and a number means that we are multiplying 10 times a number, an unknown number, meaning our variable. Well, if you look at our note up top, you'll see that whenever you're doing multiplication in algebra class, you'll want to make sure that you always show it by having a number and the variable side by side. The number's always going to come first. Therefore, I should write the number 10 and a variable right beside it. There's not a space in between them, and by doing so, it shows that you are multiplying 10 times the variable. The quotient of a number in 3. Quotient, as you know, means divide. However, we don't use the division symbol very often in algebra unless you're showing order of operations. The best way to show this is with a fraction. So we are dividing a number by 3. N divided by 3. That's what that means. Here's another example of algebraic expressions and how they might represent them in an actual real-life word problem. The number of gallons of water used to water trees is 30 times the number of trees. Well, first of all, we need to think about the things we do not know. We do not know our number of gallons of water, and we also do not know our number of trees. Therefore, we are going to have two variables. Well, I'm going to say that G is my gallons of water, and that T is my number of trees. However, when you're using T in algebra, make sure that you kind of make it with a curve at the end so you don't confuse it with a plus sign. So the equation for this says that I'm going to multiply 30 times the number of trees to get my gallons of water. Therefore, G equals 30T. The gallons of water used equals 30 times the number of trees. A second real-life example would be, what is the cost of buying several pairs of pants at $32.95 per pair? Well, as discussed on our chart, we know that per means we are multiplying. However, we do not know what our total cost is going to be, and we do not know how many pants we are actually buying. Therefore, if I am multiplying $32.95 times the number of pants I buy, I will come up with my total cost. Up until this point, we have been creating expressions rather than equations. The difference in an expression and an equation is that equations are math sentences with an equal sign. Makes sense. Equal, equation. Okay, so let's make an equation this time out of a word problem. For example, iTunes sells songs for $1.29 each. Write an equation for the total cost of a given number of songs. Well, as discussed before on our chart, each means multiply. Well, we don't know the number of songs that we're buying, and we do not know the total cost. So let's call the number of songs S and my total cost C. Well, I know if I spend $1.29 times the number of songs I buy, that will give me the total cost of my purchase. Because we have an equal sign, that was an equation. Our second example is, what is the number of slices of pizza left from an 8-slice pizza after you eat some? Well, we do not know how much we ate, but we do know how many pieces we started with, and we're trying to find how many pieces are left. So we have our 8 slices that we start with minus the amount eaten is going to equal our amount remaining. Okay, so this is something that you need to think of in realistic terms. We know that we're subtracting because we're eating some. Therefore, our pizza can't be getting bigger. It has to be getting smaller. Sometimes you're given information to create equations in the form of a table. They want you to take the information given and figure out an equation that works in every set of information. To do this, you need to think to yourself, what am I doing to the first column to get the answer in the second column? If the answers in the second column are getting bigger, you would either be adding or multiplying, right? Makes sense. The only way you can get things bigger is to add something to it or to multiply something by it. If the numbers in the second column are getting smaller, you're either subtracting or dividing. So let's look at the example we have given. We're comparing our number of hours to the distance we travel. Well, if you look here, our number of hours are increasing. 1, 3, 5. It's getting bigger. Our distance is also getting bigger. 55, 165, and 275. Because both columns are getting bigger, we are either going to be adding or multiplying to get these increased values. In order for an equation in the table to be correct, it has to work for each set of values per row. Rows go across, okay? So whatever we do has to be true for all three. So how do I get from 1 to 55? Well, I can either add 54 to 1, or I can multiply by 55. Well, if I say 3 plus 54, it's not going to equal 165. But if I say 3 times 55, it will equal 165. So adding 54 is not going to work. Well, if I say 5 times 55, that also works. Therefore, I know that I'm multiplying by 55. In order for this to be an equation, we have to use variables. Generally, the first column is your x column, and the second column is your y column. Therefore, in order to write an equation that would work for any value of x and any value of y, we would say 55 times x equals y. Now, again, just plug this in and it makes sense. 55 times 1 equals 55. 55 times 3 equals 165, and so on. As long as it's true for any value of x and any value of y, you know that you have your equation correct. Okay, so let's try another example. This time we're comparing the number of days with length. Now we don't know the length of what exactly we're measuring. We do know that it's being measured in inches. So it's not something that's extremely long. Maybe we're comparing how tall a flower grows in a certain number of days. It could be anything. They didn't give us a lot of information, but that is not the point of what we are trying to do here. What we're trying to do is figure out, again, what is happening in our first column to give us the answer in our second column. Well, as you notice, first column, again, is getting bigger, 1, 4, 8. Second column is also getting bigger, 0.45, 1.8, and 3.6. So each one is getting bigger in both columns. Therefore, we are either adding or multiplying. Well, it doesn't make much sense to start with addition because in order to get from 1 to 0.45, we would have to add a negative number, which is really the same thing as subtracting. So let's try to start with multiplication. If you are trying to multiply, well, 1 times anything is itself. So 1 times 0.45 equals 0.45. So let's try multiplying 4 times 0.45. If you plug that in your calculator, you will see that you get 1.8. 8 times 0.45 also gives you 3.6. Therefore, we know that anything we multiply by 0.45 will give us the length. So our equation should be 0.45 x equals y. Again, 0.45 times 1 gives us 0.45, and so on. If we just plug anything in our x column in the place of the equation, it will give us the answer in our y column. Now it's time to talk about real numbers and the numbers that we are including in that category. You have natural numbers, whole numbers, integers, rational numbers, and irrational numbers. All of these are in the real number category. However, they're not all the same. Your natural numbers are your counting numbers. 1, 2, 3, 4, 5, 6, and so on. The numbers that you count when you first learn how to start counting. The only difference between a whole number and a natural number is that whole numbers include 0. So you have 0, 1, 2, 3, and so on. Integers simply include positive and negative numbers. So an integer would be, for example, any number in the negative, 0, and our positive numbers. Okay, so all of those are considered integers. Rational numbers are terminating or repeating decimals. Okay? An example of a terminating decimal would be 0.5. Okay? It doesn't always have to be a decimal. The equivalent of 0.5 is 1/2. So the fraction 1/2 is also a rational number. A repeating decimal would be 0.333 and so on, repeating. The equivalent of that would be 1/3. So 1/3 is also a rational number. So rational numbers could be either a fraction or a repeating or terminating decimal. Irrational numbers are numbers we really don't like so much. They're the numbers that aren't very easy. For example, an irrational number could be pi. And we usually say that pi equals 3.14. However, pi never stops. Therefore, irrational numbers are non-repeating and non-terminating decimals. So other examples could be the square root of 7, or it could be the fraction 7 divided by 13. And I can't write that as a decimal because, like I said, it is a non-terminating, non-repeating decimal, so it would go on forever. These numbers could be positive or negative numbers as long as they don't repeat and do not terminate. So those are the different types of real numbers. Now let's actually practice classifying these types of numbers. All right, so label the following numbers with every category in which they belong. Well, all of these are real numbers, so we're not going to classify them as real numbers. We're going to do the subcategories. Well, -7 is an integer, right? It's the only number that we talked about that is a negative number without a decimal, so that's going to be an integer. The square root of 13 is an irrational number. Okay? Irrational because if you do the square root of 13 in your calculator, it is going to give you a non-terminating, non-repeating decimal. Well, now let's look at our third example, 3. This belongs to lots of categories. It could be a natural number. It could be a whole number. It could also be an integer, because all of those categories include the number 3. 0, on the other hand, cannot belong to every category just mentioned for our previous example. 0 can only be a whole number or an integer. One half was one of the examples we gave as our rational number, because 1/2 is a terminating decimal of 0.5. Therefore, it is rational. Now it's time to give you some of the terminology that we use in algebra, so you'll be familiar with the different parts of equations that we're going to be discussing. A term is a part of an expression that is added or subtracted. Okay, so there are 3 parts, or could be 3 parts of a term. A variable, which we discussed briefly earlier, is a symbol or a letter that represents one or more numbers. So anytime you see a letter, that's your variable. It stands for an unknown number. Your exponent is the power to which a variable or a number is raised. That's usually something written in superscript above, and here's an example down here that we'll talk to in a minute. Coefficient is the number in front of the variable. You cannot have a coefficient if there's not a variable attached to it. If you had a number without a variable, it would be considered your constant. Constants always go at the end of an expression. Okay? Another important thing to get in a good habit of is arrange the different terms from highest to lowest. So highest exponent to the lowest or no exponent. So in the example down here below, how many terms are in the following expression? Well, as discussed, a term is separated by an addition sign or a subtraction sign. Therefore, we have 3 terms. Now let's practice identifying the coefficients, exponents, and variables for the following terms. In the example 7x cubed, cubed means raised to the 3rd power, our coefficient is 7. It's the number in front of the variable. Our variable is x, and our exponent is 3 because it's raised to the third power. The second example, negative 8 would be your coefficient. X is the variable, and 2 is your exponent. 2x only has a coefficient and a variable. We do not have an exponent listed there. Therefore, it can be left blank. Negative 3x squared, your coefficient would be negative 3. Again, the variable is x, and your coefficient is, your exponent is 2. On 7x, again, you just have a coefficient of 7 and a variable of x. No exponents listed there. And our last example, x to the 5th power, is a little bit of a trick question. You do have a coefficient on this, even though it's not written. Anytime you see a variable by itself, it always has a coefficient of 1. So 1 is our coefficient, x is our variable, and 5 is our exponent. A very important concept in algebra is finding like terms. For something to be considered a like term, everything must match except for the coefficient, meaning your variables must match and the exponent attached to the variable must match. Any of your coefficients could be different. However, those variables and exponents must match in order for them to be considered like terms. So let's look at the example below. 13x squared plus 2x to the third minus 10x squared. Well, we need to figure out which one of these terms are like another term. So we've got an x squared, an x cubed, and another x squared. Well, like we said, you have to have the same variable and the same exponent in order for them to be a like term. Our like terms here are going to be 13x squared and 10x squared. Now keep in mind, always include the sign in front of the coefficient when combining like terms, and we're going to discuss how to combine these like terms on our next. Now we need to talk about how to combine like terms. Like terms can be added or subtracted. They're not going to be multiplied or divided, simply added or subtracted. As I discussed before, you always want to include the sign directly in front of your coefficient. Well, 3x doesn't have a sign in front of it. If it did, the only sign would be a negative. So we know that we have a positive 3x that we are combining with a positive 5x. So all you do here is add the two together. We're going to add the 3 and the 5 to give us 8, and you keep what made them alike, which was the x. So we have 3 x's plus 5 x's give us 8 x's. Second example, 8y squared s minus 3y squared s. Well, y squared s is the same on both of them. Therefore, they are like terms and can be combined. If we say 8 minus 3, we're left with 5, and then we keep what made them the same, the y squared s. So that would be our answer, 5y squared s. So here's a little bit longer example. We have m cubed minus x cubed minus 7m cubed. So now we need to think about which ones are like terms. All of these terms are raised to a third power. They have a 3 as an exponent. However, they do not all have the same variable. We have an m cubed, and then our minus 7m cubed. If we combine the two of those, we are left with negative 6m cubed, and then we just bring down the minus x cubed because minus x cubed could not be combined with anything. Therefore, that is your final answer. Often word problems make students a little nervous. However, we're going to show you how to take apart a word problem and make it much easier. So let's go ahead. First thing you always do is read the word problem all the way through before you start evaluating what they're asking you to do. You and your friends go out for sandwiches. Each sandwich is $4.45. There are 5 of you eating together. How much is the total for the sandwiches? Well, we first need to figure out what we know and what we don't know. We know that each sandwich costs $4.45. And if you look back at your chart from the beginning of our slides, each means we're multiplying. Well, how much are we multiplying by? There are 5 of us eating. Each sandwich cost $4.45, so you would simply say 5 times $4.45 to get our total cost. Well, 5 times $4.45 gives us $22.25. And you need to make sure that you say T equals and use your dollar sign because we are doing word problems, so we have to use our unit of measure. So that would be your final answer. T equals $22.25. Our second word problem. You are going to the grocery store to buy the following: 4 apples at 40 cents each, 6 oranges at 30 cents each, 4 peaches at 35 cents each, 5 pounds of grapes at $1.75 per pound, and a package of blueberries for $2.50. How much did it cost to make the fruit salad? Well, think about this. If you're buying all of this fruit, are you going to be adding the cost of all the fruit to get your total cost? Absolutely. However, you see in the problem that there are other operations that we need to do. Each, per. Those are multiplication. So our problem is going to be set up 4 times 0.40 because we're multiplying our number of apples and the cost, plus 6 times 0.30 plus 4 times 0.35 plus 5 times $1.75 plus $2.50. If you take a minute to do that in your calculator, you will see that the total cost of the fruit is going to be $16.05. So your total cost equals $16.05. The second part of the question asks, which fruit costs the most? Well, if you figured out how much the apples cost, how much the oranges cost, how much the peaches cost, the grapes, and the blueberries, you would see that the most expensive fruit was your grapes. Your least expensive fruit was your peaches. Okay, so that just gives you a little bit of an example of how you would go about shopping for the fruit and figuring out your total cost to make sure you had enough money to purchase all the different kinds of fruits that you had. The last topic that we'll be discussing in this PowerPoint is matrices. A matrix is a rectangular arrangement of numbers in rows and columns. You probably are actually much more familiar with this than you actually realize. If you've ever used Excel spreadsheets or other types of spreadsheets, you've been